Swayam Prabha. Digital India. Educated India.
So these are the basic capacitances that are present, but depending on how the voltages are applied across these two conductors, we can have an even and odd mode analysis. So even an odd mode analysis, like say initially our conductors are placed like this. This is the even mode where both these conductors are at the same potential, same positive potential. In that case, the electric field lines can be drawn as shown here. So the electric fields produced by the two conductors will actually repel each other. Now, so that's why the equivalent circuit for the even mode is even mode. Equivalent and the capacitance in between, that is C12, doesn't exist. Okay? along the line of symmetry, we will have an open. For the odd mode, now I want to say something uh, about the characteristic impedance. So recall, for each of these transmission lines, the effective capacitance is just C11 for the even mode. So recall the formula for the characteristic impedance. It is given by 1 upon VPC, right? So for the even mode, then this simply becomes like this. So this is the characteristic impedance for the even mode. Now for the odd mode, the two conductors will be oppositely charged. So the field diagram for the odd mode will be like this. So the field will be something like this, and the equivalence circuit will be so C effective is, and also note that along this line of symmetry will be short. The C effective is nothing but C11 plus 212, and so the characteristic impedance for the odd mode ZOO is equal to 1 upon VP C11 plus 212. Now, as you can see, the characteristic impedance for the odd mode, this value is different from the characteristic impedance for the even mode. And this is what is different for this coupled lines as compared to other types of couplers that we have seen. In the other type of coupler, the characteristic impedance remains the same for the odd and even mode, but for coupled line couplers, as we shall see, the characteristic impedance itself is different between the odd and even mode. So now, with this in mind, let us try to analyze the coupled line coupler. So once again, let me draw the schematic. So if we draw the even mode and the odd mode half circuits, they will simply be like this. So just like your the branch line hybrid can write the values of the reflected waves at the various ports like this. So to derive the S parameter matrix, take help of the procedure that we employed for the branch line hybrid. That is, first find the ABCD parameters. So here, since these two lines, the equivalent circuit, half circuits for the even and odd modes are just length of transmission line. So we just consider the ABCD parameters of a length of transmission line for the even and odd modes, and the ABCD parameters for a length of transmission line having electrical length theta and characteristic impedance Z0 is given like this. there was the normalized ABCD parameters. So this is the general matrix for the ABCD parameter when we consider the even and odd modes as indicated here. So then we have to add the subscripts like this. Now converting this ABCD parameters of these transmission lines to S parameters. So we have S11 even or odd is given by A so here because A and B are the same, so this equation reduces to and so this can be written as similarly S41 even and odd given by is equal to Now we want S21 is given by equal to 0. So what this means is that port 1 and 2 should be isolated and ideally S21 should be 0. Uh, so then to achieve that, so first thing we have to achieve is that the even and odd modes as given in the denominator, the S41 value for the even and odd modes, the denominator should be same for the even and odd modes. So to do this, we have to have now here this normalized Z0 and Y0s are given like for example Z0 normalized is Z0 1 Z0. So it's like Z0 is the characteristic impedance of both transmission lines, both the coupled lines, when they are just placed on their own. That is, there are no transmission lines in their vicinity. Okay, so Z0 is like the natural single conductor characteristic impedance. Okay. By the way, for coupled lines, both the transmission lines are identical. Okay, so coming back to here, now it can be shown that this equation will reduce to similarly here y0 is nothing but so this is the formula for the characteristic impedance Z0 as related to the even and odd impedances. Now once this is achieved, this condition, what it means is that S41E will be equal to S41O. So this implies this equation. And so from here, so now if we take this and apply this condition to this equation, we will have S21 equal to 0. And note that this is broadband because if we have this condition, if we have this condition met, then irrespective of the value of theta, these two terms, we will have S21 equal to 0. That is one great advantage of coupled lines that they provide broadband isolation. Okay. Similarly, let us now consider S11. So S11, which is given by this equation. So what we observe is that if uh, So first of all, if this condition is satisfied, then the denominators for the even mode and odd mode for S11 will be the same. And the parameter S11 is equal to S11 plus S11O upon 2. So from a denominator point of view, we don't have a problem if this condition is satisfied. Okay? So if we plug this condition in the denominators will be the same. What we now have to have is that the numerator, that is, if we add these two, if we add these two quantities, the numerator will be okay, and that has to be equal to 0. Okay, and what we shall see is that to satisfy this condition, also we need this condition to be true. So this condition will ensure that S11 is 0 over broadband and S21 is also 0 for broadband. Now, ideally, this will be for all frequencies. For all theta means for all frequencies, but in practice, that may not be the case. What about the through and what about S31 and S41? S31 and S41. So S31 and S41. So the formula that we had earlier stated for these two quantities, S31 is given by and S41 given by so now using the relation Z0 equal to this S and then using the values of S11 and S41 that we had derived earlier, namely these values, we can find out that S31 is given by and S41 is given by . So this is after simplifications. Okay, so what we did was we substituted the values of S41, S410, 410 and S41E from the expressions that we have derived earlier for these two quantities, and then after substituting we obtain this value. Where Kc is a measure of the difference between the odd mode and the even mode characteristic impedance. Okay, and conversely, this is the relation for, write it properly. So this is the relation between Kc and Z0E and ZOO. We can also write an alternative expression of Z0E in terms of the characteristic impedance. It is the input character. So this Z0 is the characteristic impedance of a single transmission line. That is when there is no coupled line present. So this again verifies the relation that Z0 is equal to square root of Z0 E Z0 O. So we can plot this theta versus S magnitude S31 and S41. The graph that we will get is something like this. Taking a little time to get this graph properly. Okay, and here we will have this is theta. So this is 1, that is pi by 2. This point corresponds to pi by 2. Is this point. Similarly, this point uh, corresponds to 2 of phase of pi, and so on. Okay, now this is S31 magnitude square. This is S41 magnitude square, and this purple line is the sum. Okay. So this shows that the sum of S41 square magnitude and S31 square magnitude is constant and is equal to 1. This can also follows because in a 4-port coupler, suppose power is entering port 1 and if port 2 is isolated, then power can come out only from port 3 and 4, and since the system is lossless, therefore some of the power input power will go to port 3, some of the input power will go to port 4, and so the sum of the powers entering port 3 and 4 will always be constant, and that is what this relationship, this graph shows, that is a constant. So we can, when theta is equal to pi by 2, we can write the S parameter matrix of this coupled line coupler as follows. This is what we call a symmetric coupler. It's symmetric because these S at port 3 and port 4, for example, S31 is given by Kc, but S41, S42 is given by Kc also. So means if we consider this coupler, then S31 is the same value as S41, 42. Okay. Similarly, S23 has the same value as S41. So that's why there's a symmetry between the ports 1 and 2 and 3 and 4. That's why it's called a symmetric coupler. If in addition to this, we have Kc as equal to 1 upon square root of root 2, then the S parameter matrix will be it then becomes a quad, or I can even write it like this. So this then becomes very similar to that of a quadrature hybrid coupler, branch line hybrid coupler that we discussed earlier. So this shows that this also shows these all these three matrices, this one, and this one. They show that the coupled line coupler is an example of a 90-degree coupler. So when you actually design it, what might be given to you instead of we have now analyzed it, what is actually might be given is the value of Kc and Z0. So from there, using these two relations, you can find out the value of Z0E and Z0O. So that Z0E and Z0O will help you design the spacing and the width of the transmission line. So one problem with this type of coupler is that since it is coupled line, uh, so coupled line means they are not directly connected, isn't it? Like two transmission lines are at a distance from each other. So coupled line means like this. So because they are at a distance, the coupling factor, the Kc, is not high. Values of Kc's are difficult to realize. So with that, we come to an end to the various couplers. Now I would like to show some applications of coupler. Yes, it's visible now. So let us see. So this is a network analyzer. This is the schematic of a VNA or simple network analyzer. Not a VNA stands for vector network analyzer. That has some additional circuitry for phase determination, but simple for magnitude magnitude of the return loss and insertion loss calculation, or the magnitude of the S parameters of a network. This is fine. So here this is the source. Every VNA. So VNA is a instrument used for measuring the S parameters of a network. So here the DUT represents the design under test or device under test. This is the RF source that is used. Now this is a coupler that is used. Okay. So the purpose of this coupler is to allow this input signals from the RF source, a part of it, to escape this way. So A1 here represents the incident component of the RF source. Now, because this port is isolated with respect to this input port, so no part of this input signal will appear at here. Okay. Now, after this A1, a component of this A1 also travels to the DUT, and there is a reflection B1. But this B1 will not affect this A1 that is in this port, because these two ports are also isolated. So as a result, you will have a component of B1 here and A1 here, and so you can know exactly what are the incident and reflected waves. You can measure these. So this is a way of completely separating the incident and reflected waves, whereas we have seen that it's not so easy in a normal transmission line to separate the incident and reflected waves. Here, using this coupler, we can completely separate them. Now this represents the output circuit, and the configuration is simple. We are separating A2 and B2. This way, once we know, we can find out the magnitude of all the S parameters of this two-port network. So the next application uh, of second, there may be other applications. I'm just listing a few. Is an IQ modulators. So IQ modulators, as we know, are used in communication to generate quadrature and quadrature and in phase components. So this I and Q signals are 90-degree phase shifted. And this is where these quadrature or 90-degree couplers come in handy. So here we have the LO, the local oscillator signal. At this end, we will have a 90-degree phase shift with respect to this end. This can then be multiplied by the I signal, and this is multiplied by the Q signal, and then we use a combiner. A combiner is the opposite, is exactly same as a power divider, except that instead of dividing power, we combine two power sources. So combiner and power divider are exactly the same thing. It's just the way we apply the input is different. So now we using this combiner, we combine the signal in this branch with the signal in this branch to obtain the combined signal. So this is then example of modulator. Then we also have a demodulator. So given an RF signal as like this, how can we recover the baseband signals I and Q? So here again we pass the signal. First we obtain two quadrature signals using this coupler and then multiply them with the RF input, this RF signal. Okay. So this signal is multiplied with the quadrature component and the in-phase component, and then they are passed to an integrator or low pass filter to obtain the I and Q signals. This is another application of couplers. So in order to provide broadband matching of amplifiers, which is not always possible by simple amplifier design. So this is a mechanism by which any reflected signal from the amplifier is diverted in a different direction. So the construction is like this, that we have two identical amplifiers connected like this as shown. So this is one disadvantage of balanced amplifiers, that we need two identical amplifiers. Then at the input we apply the input signal. Now it can be shown that even though the incident signal will be divided equally among these two amplifiers, the reflection that happens at the input will be directed to this port 2. So that way no amount of the reflected signal will appear at this one double dash port. And so it's not a true impedance matching, but it gives the appearance of broadband matching. Similarly, the same technique is applied at the output port. The other application is in balanced filters. So filters are cannot be matched at all frequencies, right? Because suppose these two are high pass filters, then they will pass high frequency signals but not allow low frequency signals. So for low frequencies, these filters cannot provide matching by definition. So what this mechanism does is very similar to the balanced amplifier mechanism. Suppose you input signals here. These high pass filters will allow the high frequency signals to pass through them, and the low frequency signals that will be reflected at the input of these high pass filters can be shown mathematically to be diverted at this port. And this way we obtain matching for all frequencies. So the high pass signals will pass to this port and the low pass signals will be reflected back to this port. So with that we come to an end to couplers. So perhaps in the next lecture we'll start with filters. Thank you.